Hello and welcome. Tonight, we'll be exploring a question that becomes more fascinating the longer you sit with it. Could the universe be far stranger than we imagine? At first glance, the universe can seem familiar. The sun rises each morning. The moon follows its gentle path across the sky. The stars appear steady and predictable, just as they did for countless generations before us. Yet every time humanity has found a new way to look deeper into the cosmos, the universe has surprised us. Again and again, what seemed simple turned out to be mysterious. What seemed complete turned out to be only the beginning. So, find a comfortable place to rest and let your thoughts drift upward, beyond the rooftops and city lights, beyond the clouds, and into the vast darkness above. For most of human history, the night sky was the entire universe. Ancient people looked upward and saw patterns among the stars. They imagined gods, heroes, animals, and stories stretching across the heavens. The sky appeared like a great dome overhead, with Earth resting quietly at its center. It was a reasonable picture. After all, nothing in everyday experience suggested otherwise. The ground beneath your feet feels still. The sun appears to travel across the sky. The stars rise and set in a reliable rhythm. For thousands of years, humanity's view of the cosmos was shaped by what could be seen with the naked eye. Then something remarkable happened. We began building tools. The first telescopes were simple by modern standards. Yet when people pointed them toward the sky, they discovered that the universe was not what they had imagined. The moon was not a perfectly smooth sphere. Jupiter had moons of its own. The Milky Way was not a cloudy streak painted across the heavens. It was made of countless stars. Each new discovery expanded the boundaries of reality, and every expansion revealed something unexpected. Today, our telescopes are vastly more powerful than those early instruments. They can see galaxies billions of light years away. They can detect invisible forms of radiation. They can even glimpse light that began its journey when the universe itself was still young. Yet, despite all of this progress, there is a surprising limit to what we can observe. Imagine standing on a quiet beach. You look out across the ocean. The water stretches in every direction until it reaches the horizon. From where you stand, the horizon feels like the edge of the world. But you know it is not truly an edge. It is simply the farthest distance you can see. The universe has something similar. Astronomers call it the observable universe. This does not mean it is the entire universe. It only means it is the portion whose light has had enough time to reach us since the cosmos began expanding roughly 13.8 billion years ago. In other words, we can only see as far as light has been able to travel. Everything beyond that remains hidden. Perhaps temporarily, perhaps forever. This idea can feel strange at first. When you look at a distant galaxy through a telescope, you are not seeing it as it exists right now. You are seeing ancient light, light that may have traveled for millions or even billions of years before reaching Earth. In a sense, every telescope is also a time machine. The farther it looks into space, the farther it looks into the past. A nearby star may appear as it was a few years ago. A distant galaxy may appear as it was before Earth even existed. Some of the oldest light we can observe has been traveling across space for nearly the entire history of the universe. It surrounds us even now, quietly filling the cosmos like a faint echo from an unimaginably distant past. Yet even this ancient light does not reveal everything. There are regions so distant that their light has not reached us, and because space itself is expanding, some regions may never become visible. This is where the story becomes even more curious. When most people imagine expansion, they picture objects moving through space. But on cosmic scales, it is space itself that stretches. A useful image is a loaf of raisin bread rising in an oven. As the dough expands, every raisin appears to move away from every other raisin. The raisins are not racing through the dough itself is growing. In a similar way, galaxies are carried apart as space expands between them. Over immense stretches of time, this expansion creates a cosmic horizon. Beyond that horizon lie regions we cannot reach with our observations. No matter how advanced our technology becomes, some parts of reality may remain permanently hidden. This realization can feel a little unsettling. Yet, it can also be beautiful. There is something humbling about knowing that the universe is larger than our view of it. Even after centuries of astronomy, after rockets, space probes, giant observatories, and orbiting telescopes, we may still be seeing only a small fraction of what exists. Imagine walking into a vast library in the middle of the night. A single lamp illuminates the nearest shelves. You can read the books within that circle of light. You can learn from them. You can spend a lifetime exploring them. But beyond the glow, countless shelves disappear into darkness. You know they are there. You simply cannot see them. The observable universe may be something like that lamp-lit corner of an immeasurably larger library, a place filled with wonders, yet surrounded by mysteries we cannot yet reach. And perhaps that is what makes the universe so endlessly fascinating. Not merely its size, not merely its age, but the possibility that every answer leads to a larger question. The stars above us may seem familiar, yet beyond their gentle light lies a reality far stranger than anyone standing beneath an ancient sky could have imagined. And the deeper we travel into that reality, the closer we come to the moment when everything we know first began. When we look across the observable universe, we see an astonishing variety of things: stars, galaxies, nebulae, clusters of galaxies stretching across unimaginable distances. Yet if we travel backward through cosmic history, all of that complexity gradually begins to fade away. Galaxies become younger, stars become rarer, atoms themselves eventually disappear. The deeper we look into the past, the simpler the universe becomes, or at least it seems to. Modern astronomy tells us that the universe has been expanding for roughly 13.8 billion years. This conclusion emerged from one of the most important discoveries in science. When astronomers examined distant galaxies, they found that nearly all of them appeared to be moving away from us. At first, this might sound as though Earth occupies some special position in the cosmos. But that is not what was happening. A better way to imagine it is to picture dots drawn on the surface of a balloon. As the balloon slowly inflates, every dot moves farther away from every other dot. No single dot is the center of the expansion. The surface itself is stretching. Something similar happens throughout the universe. Space expands. Here, and if everything is moving apart today, then running the story backward suggests that everything was once much closer together. This realization eventually led scientists to the idea that we now call the Big Bang. Despite the name, the Big Bang was not an explosion that happened somewhere in space. It was the rapid expansion of space itself. There was no empty cosmic room waiting for the universe to explode into. The expansion created the space through which everything would later travel. This can be difficult to picture because every explosion we experience in daily life happens within a pre-existing environment. A firework explodes in the sky. A volcano erupts on Earth. But the beginning of the universe was something fundamentally different. Space was not expanding into anything we can easily imagine. Space itself was changing. As strange as that sounds, the story becomes even stranger. According to current theories, the early universe may have experienced an extraordinarily brief period of expansion known as cosmic inflation. During this fleeting moment, the universe expanded at a rate so astonishing that ordinary language struggles to describe it. A region smaller than an atom may have grown into something vastly larger in a tiny fraction of a second. To visualize this, imagine drawing a tiny dot on a balloon. Then imagine that balloon suddenly expanding until the dot becomes larger than an entire city. The details are very different, of course, but the image captures the spirit of what inflation suggests. This brief episode may explain several mysteries that puzzled cosmologists for decades. It may also have laid the foundations for everything we see today, because during those earliest moments, the universe was not perfectly smooth. Tiny fluctuations existed, tiny irregularities, tiny differences. At first glance, they might seem insignificant, the sort of imperfections you would normally ignore. Yet, these microscopic variations may have changed everything. Imagine a calm pond on a windless morning. Its surface appears almost perfectly flat, but even the smallest ripple can influence the pattern of the water. In a similar way, tiny fluctuations in the infant universe may have provided the seeds from which galaxies eventually grew. Every star, every planet, every galaxy, perhaps even every living thing, may ultimately trace its origins back to these ancient fluctuations. The thought is both humbling and beautiful. The largest structures in existence may have begun as the faintest whispers of difference in the earliest moments of time. Evidence for this ancient history still surrounds us. It arrives from every direction in the sky, not as visible light, but as a faint glow that fills the universe. Astronomers call it the cosmic microwave background. You can think of it as the oldest light we can observe, a gentle AF long before stars illuminated the darkness, long before galaxies spiraled across the cosmos. This ancient radiation has traveled for billions of years to reach us. Today, sensitive instruments can detect it with remarkable precision. When scientists map this primordial light, they discover subtle patterns, tiny variety, tiny temperature differences. These patterns reveal clues about the fluctuations that existed near the beginning of cosmic history. In a sense, they provide a baby picture of the universe, a glimpse of reality when everything was still in its earliest stages of development. Yet despite all we have learned, one question continues to capture the imagination. What happened before the Big Bang? It seems like a natural question. After all, every event in ordinary life has something that came before it. A tree grows from a seed. A river begins from rainfall. A book begins with an author. So it feels intuitive to ask what existed before the universe began. The challenge is that time itself may be part of the universe's story. If time emerged together with the cosmos, then asking what happened before the beginning may be a little like asking what lies north of the North Pole. The question assumes a direction that may not exist. Some physicists have proposed that the universe has no true beginning in the conventional sense. Others suggest that our universe emerged from an earlier cosmic phase. There are theories involving cosmic cycles, where expansion is followed by contraction and then renewal. There are ideas in which a previous universe collapsed before giving rise to another. There are proposals suggesting that what we call the Big Bang may have been a transition rather than an absolute beginning. At the moment, no single answer has been confirmed. The universe guards its earliest secrets carefully, and perhaps that uncertainty is part of what makes the story so captivating. The deeper we travel toward the beginning, the more familiar concepts begin to dissolve. Space behaves differently, time becomes difficult to define, and reality itself starts to resemble something far more mysterious than our everyday experience prepares us for. Those first moments may seem impossibly distant, yet the traces they left behind still shape everything we see today. From galaxies scattered across the heavens to the stars shining quietly above us, the universe continues to carry the memory of its earliest beginnings. And as the cosmos expanded and cooled, those first seeds of structure slowly grew into something magnificent. As the universe continued to expand and cool, the simple cosmos of its earliest moments slowly began to change. The ancient glow that filled space gradually faded. The first atoms formed. For a long time, darkness ruled the universe. There were no stars, no galaxies, no planets, no familiar points of light scattered across the heavens. Only vast clouds of hydrogen and helium drifting through expanding space. It was a quiet universe, a universe waiting for something to happen. Over millions of years, gravity began its patient work. Tiny differences in density, inherited from those ancient fluctuations we explored earlier, slowly grew larger. Regions containing slightly more matter exerted slightly stronger gravitational pull. They attracted more material, which increased their gravity, which attracted even more material. Little by little, structure began to emerge. Imagine watching snow fall onto a wide field. At first, the snow lands almost evenly, but small drifts eventually appear. Once a drift begins to form, it catches more snow, and as it grows larger, it gathers even more. Gravity worked in a similar way across the young universe. The smallest differences gradually became enormous structures. Eventually, enough matter collected together to ignite the first stars. These early stars may have been unlike most stars we see today. Many astronomers believe they were extraordinarily massive. Some may have been hundreds of times heavier than our sun. Others may have shone millions of times brighter. They lived fast and died young. Yet their brief lives transformed the cosmos. Inside their blazing interiors, the first heavy elements were forged. The carbon in your body, the oxygen you breathe, the calcium in your bones. Much of it was created inside ancient stars that lived and died billions of years before Earth existed. In a very real sense, every person is connected to those forgotten suns. As more stars formed, they gathered into larger systems. Galaxies began to appear. At first, these galaxies were small and irregular. Over immense stretches of time, they merged, collided, and grew. Some evolved into elegant spirals. Others became enormous elliptical galaxies containing trillions of stars. From our perspective, galaxies can seem scattered randomly throughout the universe. But when astronomers mapped larger and larger regions of space, they discovered something unexpected. The universe possesses an enormous hidden architecture, a structure so vast that it challenges the imagination. This structure is known as the cosmic web. Rather than being distributed evenly, galaxies gather along gigantic filaments that stretch across hundreds of millions of light years. These filaments intersect like roads connecting distant cities. At the intersections, galaxy clusters form. Some clusters contain hundreds or even thousands of galaxies. Between these regions lie immense cosmic voids, areas so empty that they contain relatively few galaxies compared to the crowded regions around them. To visualize this, imagine looking at a spider web covered with morning dew. The droplets of water cling to the strands. The spaces between the strands remain mostly empty. The universe appears surprisingly similar. Galaxies are like the droplets. The cosmic web forms the underlying framework, and the vast voids occupy most of the space in between. The scale of these structures is difficult to fully appreciate. Some cosmic formations stretch across distances so large that even light requires hundreds of millions of years to cross them. There are enormous structures with names like the Sloan Great Wall and the Giant Arc. Their dimensions span billions of light years. They are among the largest known structures in the observable universe. And yet, even these colossal formations may represent only a tiny portion of a much larger cosmic landscape. Some researchers have even suggested that our region of space may sit near a giant cosmic void. If true, this could subtly influence certain observations of the universe. The idea remains an active area of research, but it serves as a reminder that our cosmic address may be more unusual than we realize. One of the most intriguing discoveries in recent years emerged when scientists compared the cosmic web with something much closer to home: the human brain. At first glance, the comparison sounds almost poetic. After all, what could possibly connect galaxies separated by millions of light years with neurons inside a human skull? The answer is not that the universe is literally a giant brain. There is no evidence for such a claim. Yet when researchers examined the statistical patterns of both systems, they found surprising similarities. Both consist of dense regions connected by filaments. Both contain clusters linked through vast networks. Both display complex structures emerging from relatively simple underlying rules. The resemblance is not perfect, nor does it imply a deeper connection, but it highlights something fascinating. Nature often creates similar patterns at vastly different scales. A river branches across a landscape. Tree roots spread through soil. Lightning forks through the sky. Neurons form networks, and neurons form networks inside the brain. Again and again, the universe seems to favor patterns that repeat across scales. The same reality that builds galaxies also builds coastlines, clouds, rivers, and living systems. The deeper we look, the more these echoes begin to appear. Yet one mystery remained. Astronomers soon realized that the visible matter inside galaxies could not fully explain the structures they observed. There simply was not enough ordinary matter, not enough stars, not enough gas, not enough dust. Something unseen seemed to be helping gravity shape the cosmos. Although we will explore this invisible component more deeply later, its influence is already present here. Many scientists believe that enormous filaments of dark matter helped guide the formation of the cosmic web itself. You can imagine dark matter as an invisible framework beneath a building. The framework cannot be seen from the outside, yet it quietly supports everything resting above it. Galaxies may have formed along these hidden gravitational pathways, gathering where dark matter had already created favorable conditions. Without that invisible structure, the universe we know might look very different. Perhaps galaxies would never have formed so efficiently. Perhaps stars would be far rarer. Perhaps planets like Earth would never have appeared at all. It is remarkable to think that some of the most important influences in cosmic history may be completely invisible. Even more remarkable is the scale on which these influences operate. Imagine shrinking the Milky Way galaxy to the size of a grain of sand. On that scale, many of the great cosmic structures would still be larger than entire continents. Human intuition evolved to understand forests, mountains, rivers, and oceans. It did not evolve to understand structures spanning hundreds of millions of light years. And yet, through observation, mathematics, and imagination, humanity has managed to uncover them. There is something deeply moving about that achievement. A species living on a small, rocky planet, orbiting an ordinary star, has learned to map structures so vast that they challenge the limits of language itself. The cosmic web is not directly visible when you look up at the night sky. You cannot see its filaments stretching across the darkness. You cannot watch galaxy clusters gathering at its intersections. Yet those structures are there, quietly shaping the universe on the largest scales. If you could somehow travel far beyond our galaxy, far beyond our local group of galaxies, and continue outward for unimaginable distances, you might eventually witness the grand design in its entirety. You would see luminous rivers of galaxies flowing across space. You would see enormous empty regions larger than thousands of galaxies combined. You would see a cosmos that resembles a living network more than a random scattering of stars. And perhaps the most surprising part of all is that this magnificent architecture emerged from tiny beginnings. The vast cosmic filaments, the galaxy clusters, the superclusters, the enormous voids, all of them ultimately trace their origins back to minute fluctuations in the early universe. Tiny differences became giant structures. Simple beginnings gave rise to extraordinary complexity. The story carries a quiet lesson that appears throughout nature. Small changes, given enough time, can create remarkable outcomes. A seed becomes a forest. A snowflake becomes a glacier. A tiny fluctuation becomes a galaxy. And a universe that once seemed almost uniform becomes a vast cosmic web stretching across billions of light years. Yet even this immense structure is only part of the story, because much of the framework holding the cosmos together remains invisible. The galaxies we see may be only the illuminated surface of something far larger, something hidden, something that passes silently through space, through stars, through planets, and even through our own bodies without leaving a trace. To understand why galaxies move the way they do, and why the cosmic web exists at all, we must turn our attention toward one of the greatest mysteries in modern science. A mystery that may account for far more of the universe than everything we can see. If you walked outside on a calm day and watched the branches of a tree swaying back and forth, you would naturally assume that something was moving them. Even if you could not see the wind itself, the motion would reveal the presence of an invisible force. In many ways, the story of dark matter began with a similar observation. Astronomers looked at galaxies and noticed that something unseen seemed to be influencing them. The stars were moving too quickly. The galaxies were holding together too well. Gravity appeared stronger than the visible matter could explain. At first, this seemed impossible. After all, galaxies contain enormous numbers of stars. Our own Milky Way contains hundreds of billions of them. Surely that should be enough. Yet when scientists carefully measured how stars orbit within galaxies, they discovered a puzzle. The outer stars were moving much faster than expected. According to the gravity produced by visible matter alone, Many of those stars should have escaped their galaxies long ago. But they did not. They remained in orbit. Something else was providing additional gravitational pull, something invisible. One of the most important figures in this story was Vera Rubin. During the 20th century, she studied how galaxies rotate and found compelling evidence that enormous amounts of unseen matter must exist around them. Her observations helped transform a strange possibility into one of the central mysteries of modern cosmology. Today, scientists call this invisible substance dark matter. The name can sound dramatic, almost mysterious, yet the term simply means that it does not emit, absorb, or reflect light in a way we can easily detect. We cannot see it directly. We infer its existence through gravity. Imagine arriving in a forest after fresh snowfall. You notice footprints crossing the snow. Although the traveler is gone, the tracks reveal that someone passed through. Dark matter is a little like those footprints. We do not observe the substance directly. Instead, we observe its gravitational effects. Those effects appear everywhere, around galaxies, inside galaxy clusters, across the vast filaments of the cosmic web. In fact, current estimates suggest that ordinary matter, the matter making up stars, planets, oceans, mountains, trees, and people, accounts for only a small fraction of the universe. Everything familiar belongs to a surprisingly tiny category. The overwhelming majority of cosmic matter appears to be invisible. That realization can feel almost unbelievable. For centuries, humanity assumed that what we could see represented most of reality. Modern astronomy has revealed something very different. The visible universe may be only the illuminated surface of a much larger hidden structure. A useful image is that of a city at night. From an airplane, you might see streets, buildings, and glowing windows. Yet much of the city's structure remains hidden in darkness. The foundations beneath buildings, the pipes beneath roads, the electrical systems behind walls. The visible lights reveal only part of the whole. Dark matter may play a similar role in the cosmos. Many astronomers describe it as a gravitational scaffolding, a hidden framework that helped galaxies form and continues to hold large structures together. Without it, the universe might look profoundly different. Perhaps galaxies would never have gathered into their present shapes. Perhaps stars like our sun would be far less common. One particularly fascinating aspect of dark matter is that it may be passing through you right now, not because it is dangerous, not because it is unusual, but because it appears to interact very weakly with ordinary matter. If dark matter particles exist in the forms many physicists suspect, then countless numbers of them may drift through Earth every second, through mountains, through oceans, through entire planets, and through our own bodies, silently, continuously, without us noticing. It is a strange thought. Invisible visitors crossing the world every moment, leaving almost no trace behind. And yet dark matter is not the only mystery. In recent decades, astronomers uncovered another puzzle. This one even more surprising. As telescopes improved, scientists became increasingly confident that some ordinary matter was missing. Calculations based on the early universe suggested a certain amount of matter should exist, but observations seemed to find only part of it. For years, a significant fraction appeared to be unaccounted for. This became known as the missing matter problem. Eventually, clues began to emerge from an unexpected source: fast radio bursts. These are brief flashes of radio energy arriving from distant galaxies. They last only an instant. Yet during their journey, they pass through enormous regions of intergalactic space. By studying how these signals travel, Astronomers discovered evidence that much of the missing matter was hiding in vast clouds of extremely thin gas between galaxies, not concentrated in stars, not concentrated in planets, but spread across the enormous spaces separating cosmic structures. Another mystery awaited, and this one may be even stranger than dark matter. For much of the 20th century, scientists assumed that gravity should gradually slow the expansion of the universe. After all, gravity attracts. It pulls objects together. A cosmic expansion should eventually begin losing momentum. Yet observations revealed the opposite. The expansion is accelerating. Galaxies are not merely drifting apart. On the largest scales, they are moving away from one another at an ever-increasing rate. Something appears to be pushing the universe apart, or more accurately, something seems woven into space itself. Astronomers call this phenomenon dark energy. Unlike dark matter, which helps pull structures together through gravity, dark energy appears connected to the expansion of space. It remains one of the greatest unsolved mysteries in science. Some physicists suspect it may be related to vacuum energy. This idea begins with another surprising discovery. Empty space is not truly empty. Even the quietest vacuum contains activity at the quantum level. Tiny fluctuations, brief appearances and disappearances of particles. Subtle energy woven into the fabric of reality itself. Whether this vacuum energy explains dark energy remains uncertain. The numbers predicted by theory and the numbers observed in nature remain dramatically different. It is one of the largest disagreements between theoretical expectations and observational measurements in all of physics. And so we find ourselves in an extraordinary situation. After centuries of exploration, humanity has mapped galaxies across billions of light years. We have traced the cosmic web. We have observed ancient light from the early universe. Yet when we add everything together, the conclusion is astonishing. Most of the cosmos remains unknown. Most of the universe appears to consist of things we cannot directly see and do not fully understand. Dark matter, dark energy, invisible influences shaping the fate of everything. The stars overhead may seem familiar, but beneath that familiar appearance lies a reality filled with hidden structures and unanswered questions. And among the most fascinating objects born from those hidden forces are some of the strangest creations in the universe, worlds that wander alone through darkness, stars that pulse like cosmic heartbeats, and celestial objects that challenge everything we think we know about nature. As we journey deeper into the cosmos, it becomes increasingly clear that the universe rarely follows our expectations. Many of us grow up imagining planets as places like Earth, worlds orbiting stars, warm sunlight falling across landscapes, predictable days and nights. But the universe has a remarkable habit of creating things far stranger than our imagination first allows. Consider for a moment a lonely planet drifting through darkness. No sunrise, no sunset, no parent star illuminating its skies, no familiar rhythm of day and night. Astronomers call these wandering worlds rogue planets. Unlike Earth, Mars, or Jupiter, rogue planets travel through interstellar space without orbiting a star. Some may have been ejected from young planetary systems long ago. Gravitational encounters can be surprisingly chaotic. A close pass between giant planets may fling one world outward, sending it into the darkness between the stars. Once expelled, a rogue planet begins a solitary journey that may last billions of years. Imagine standing on such a world. There would be no bright sun crossing the sky. The heavens would be dominated by distant stars, appearing far more numerous than those seen from Earth. the landscape might remain frozen beneath endless darkness. Yet some scientists have suggested that certain rogue planets could still retain internal heat, hidden beneath thick layers of ice. In such places, warmth from deep within the planet could potentially sustain underground oceans. Life, if it exists there, would experience a universe very different from our own. The cosmos also appears capable of producing worlds that sound almost mythical. Among the most famous examples are the so-called diamond planets. These are not giant gemstones floating through space, as popular illustrations sometimes suggest. Rather, they are worlds whose internal composition may contain enormous quantities of carbon compressed under immense pressure. Deep beneath their surfaces, carbon may crystallize into diamond-like structures on scales difficult to comprehend. The idea sounds like something from fantasy, yet nature often proves more creative than fiction. Elsewhere, astronomers have discovered evidence for ocean worlds. Planets where vast quantities of water may cover much of the surface. Others appear to be lava worlds, with temperatures so extreme that parts of their surfaces may glow with molten rock. Some orbit so close to their stars that entire landscapes may resemble gigantic volcanic seas. The diversity of planets discovered during the last few decades has transformed our understanding of what a world can be. The solar system no longer serves as the only template. Nature offers countless variations, and perhaps some surprises remain undiscovered. One such mystery is the possibility of Planet 9. Astronomers have noticed unusual patterns in the orbits of several distant objects beyond Neptune. One possible explanation is that a large, undiscovered planet may lurk far from the Sun, moving through regions of space we have not yet fully explored. Its existence remains uncertain. No direct observation has confirmed it. Yet the search continues. Even within our own cosmic neighborhood, mysteries endure. There is also an intriguing idea that our Sun may once have had a stellar companion. Many stars form in pairs. Some astronomers have suggested that billions of years ago, the Sun may have been born alongside a sibling star. If so, that companion eventually drifted away, becoming just another distant star among countless others in the galaxy. The thought carries a certain quiet poetry, a long-lost sibling wandering somewhere within the Milky Way. As fascinating as planets may be, stars remain the true architects of cosmic history. The earliest stars were unlike most stars alive today. Astronomers often refer to them as the first generation of stars. Formed from the simple ingredients available after the universe's earliest moments, these ancient suns may have been extraordinarily massive. Many likely burned with astonishing brightness. Their lives were brief but transformative. Inside their cores, new elements were forged. When they died, those elements spread into space, enriching future generations of stars and planets. Without those early stellar pioneers, the ingredients required for life would not exist. Some stars live alone, others share their lives with companions. Binary star systems are surprisingly common throughout the galaxy. In these systems, two stars orbit one another in a slow gravitational dance. Sometimes the relationship becomes dramatic. If one star expands as it ages, material may begin flowing toward its companion. Astronomers sometimes describe this process as stellar cannibalism. Matter from one star gradually feeds another. The result can produce spectacular outbursts and unusual stellar behavior. Certain stars also pulse rhythmically, growing brighter and dimmer in regular cycles. These stellar heartbeats helped astronomers measure distances across the universe and played a crucial role in understanding the true scale of the cosmos. Yet among the most extraordinary stellar remnants are neutron stars. When a massive star exhausts its fuel and collapses, gravity crushes its core with unimaginable force. The result can be an object containing more mass than our sun compressed into a sphere roughly the size of a city. To appreciate how extreme this is, imagine compressing a mountain into something small enough to fit inside a room. The densities inside neutron stars are almost beyond human intuition. Matter exists there in forms rarely found elsewhere in nature. Some neutron stars become pulsars. As they rotate, powerful beams of radiation sweep through space. If one of those beams crosses Earth, astronomers detect regular pulses. The effect resembles a lighthouse standing on a distant shore. Each rotation sends another flash across the darkness. Some pulsars spin at astonishing speeds, hundreds of rotations every second. Their precision rivals the finest clocks humanity has ever built. Across the galaxy, these spinning remnants keep time with remarkable consistency. And then there are magnetars. If neutron stars are extreme, magnetars push even further. These objects possess magnetic fields so powerful that they rank among the strongest known phenomena in the universe. A magnetar is the kind of object that reminds us how far nature can travel beyond everyday experience. The universe is filled with worlds that wander without stars, planets made of unfamiliar materials, ancient suns brighter than anything alive today, stellar remnants spinning like cosmic beacons. And yet, even these remarkable objects are not the most extreme creations in existence. For when the largest stars finally reach the end of their lives, gravity can produce something even stranger. Something so powerful that it bends space, slows time, and challenges our deepest understanding of reality itself. By the time a massive star reaches the end of its life, it has already spent millions of years performing one of the universe's most important tasks. It has generated light. It has forged elements. It has helped shape its surrounding region of space. Yet for some stars, the final chapter becomes far more dramatic than anything that came before. When a very massive star exhausts its nuclear fuel, gravity begins to take control. For most of the star's life, an invisible balance exists. Gravity constantly pulls inward. Meanwhile, energy produced in the star's core pushes outward. These two influences compete with one another, maintaining stability. But eventually, the fuel runs low. The outward pressure weakens. Gravity gains the upper hand, and the star begins to collapse. The collapse happens with astonishing speed. Layers of matter rush inward. Temperatures soar. Pressures become extreme. In some cases, the collapsing core forms a neutron star. In others, gravity continues compressing matter beyond even that remarkable state. The result is a black hole. Black holes are often portrayed as cosmic vacuum cleaners, endlessly sucking everything around them into oblivion. The reality is more subtle. If our sun were somehow replaced by a black hole of equal mass, Earth's orbit would remain almost unchanged. The planet would continue moving around the black hole, much as it currently moves around the sun. The difference would be darkness, not a stronger gravitational pull at Earth's distance. Black holes are strange not because they possess magical gravity, but because their mass becomes concentrated within an extraordinarily small region. This creates conditions unlike anything we encounter in everyday life. At the boundary of every black hole lies a region known as the event horizon. You can think of it as a point of no return. Imagine a river flowing toward a great waterfall. Far upstream, a boat can still turn around and escape. Closer to the waterfall, the current becomes stronger. Eventually, there comes a point where no amount of rowing can overcome the flow. Beyond that point, the journey becomes inevitable. The event horizon is somewhat similar. Crossing it does not involve hitting a wall. There is no visible barrier. Yet once something passes beyond that boundary, escape becomes impossible according to our current understanding of physics. One of the strangest consequences of black holes involves time itself. According to Einstein's theory of gravity, massive objects influence the flow of time. Near a black hole, this effect becomes extraordinary. To a distant observer, clocks near the black hole appear to run more slowly. Minutes experienced close to the black hole could correspond to much longer periods far away. This is not science fiction. Time dilation has been confirmed through many experiments involving weaker gravitational fields. Black holes simply push the effect to an extreme. The universe, it seems, does not provide a single universal clock. Time flows differently, depending on where you are. Among the most remarkable black holes are the supermassive giants found at the centers of galaxies. Our own Milky Way contains one. Although invisible directly, astronomers have tracked stars orbiting around an unseen object in the galactic center. Their motions reveal the presence of a black hole containing millions of times the mass of our Sun. And our galaxy is not unusual. Many galaxies appear to harbor similar giants. Some contain black holes billions of times more massive than the Sun. For decades, black holes remained objects that scientists could only infer indirectly. Then, in 2019, something extraordinary happened. Humanity obtained its first image of a black hole's shadow. This achievement required telescopes spread across Earth, working together as a single virtual instrument. The resulting image revealed a glowing ring surrounding a dark central region. For the first time, one of the most mysterious predictions of modern physics had been observed in a direct and striking way. It was a moment that connected generations of scientific effort. From Einstein's equations to modern observatories, the idea had traveled from theory to observation. Yet black holes still had more surprises waiting. In 2015, scientists detected gravitational waves for the first time. These waves are tiny ripples in the fabric of space itself. They were produced when two black holes spiraled together and merged. The event released enormous amounts of energy, sending waves outward across the universe. By the time those waves reached Earth, they were incredibly faint. Yet instruments known as LIGO were sensitive enough to detect them. For the first time, humanity was not merely looking at the universe. Humanity was listening to it. It was as though a new sense had suddenly become available. The cosmos could now be explored through vibrations as well as light. And black holes may not all share the same origin. Some researchers have proposed the existence of primordial black holes. Unlike ordinary black holes formed from dying stars, these hypothetical objects may have emerged during the universe's earliest moments. They could have formed before the first stars existed, before galaxies, before planets, perhaps even before the cosmic web began taking shape. No direct evidence has yet confirmed their existence. Yet they remain an intriguing possibility. Some theories even suggest they could contribute to the mystery of dark matter. Another surprise emerged from the work of the physicist Stephen Hawking. For many years, black holes were thought to be completely black, objects that only absorbed, never emitted. Hawking showed that quantum effects may allow black holes to slowly radiate energy. Over unimaginably long periods, This process could cause black holes to gradually evaporate. The idea transformed how physicists think about these objects. It also led to one of the deepest puzzles in modern science: the information paradox. Suppose a book falls into a black hole. The atoms disappear beyond the event horizon. Eventually, the black hole may evaporate through Hawking radiation. What happens to the information describing the book? Is it destroyed? Preserved somehow? Encoded in ways we do not yet understand? The answer remains uncertain, and it touches some of the deepest foundations of physics itself. Black holes are therefore much more than exotic astronomical objects. They are laboratories for some of the universe's biggest questions. Questions about gravity, questions about quantum mechanics, questions about time, questions about information and reality. The deeper scientists investigate black holes, the more they discover connections between the largest structures in the cosmos and the smallest processes in nature. It is as though these dark objects sit at a crossroads where different parts of physics meet. And beyond that, crossroads lies an even deeper mystery. Because when physicists examine reality at its smallest scales, they encounter a universe every bit as strange as the one revealed by black holes. Black holes reveal a universe that bends space and slows time. Yet when physicists turn their attention in the opposite direction, toward the smallest scales imaginable, they encounter mysteries that are just as profound. In some ways, they are even stranger. For centuries, people imagined that if you continued dividing matter into smaller and smaller pieces, you would eventually arrive at tiny, solid building blocks, little cosmic bricks from which everything else was made. Modern physics paints a far more surprising picture. According to our best theories, reality is not fundamentally built from solid objects. Instead, the universe appears to be filled with fields, invisible fields stretching throughout all of space. Particles are not separate objects moving through empty space in quite the way we often imagine. They are more like ripples appearing within these underlying fields. A useful comparison is the surface of a calm lake. When a wave moves across the water, the wave is not separate from the lake. It is a pattern within the lake. Similarly, what we call particles may be patterns within deeper fields that permeate the universe. This idea already feels unusual, but it leads to an even stranger realization. Empty space is not truly empty. Imagine entering a quiet room late at night. The room seems still. Nothing appears to be happening. Yet, if you listen carefully, you might notice faint sounds, a distant hum from an appliance, the soft movement of air, the building settling almost imperceptibly. What first appeared completely silent turns out to contain subtle activity. Physicists have discovered something similar about the vacuum of space. Even regions that appear empty are not perfectly inactive. Tiny fluctuations constantly occur at the quantum level. Brief events unfold continuously beneath the surface of reality. Some of these fluctuations can be described as pairs of particles appearing and disappearing over incredibly short intervals. They are often called virtual particles. The name can sound mysterious, but the important idea is simple. The vacuum is not a featureless void. It is dynamic, restless, alive with microscopic activity. You would never notice these fluctuations while walking through a park or drinking a cup of tea. Yet, according to modern physics, they are happening everywhere, at every moment, throughout the entire universe. This raises a fascinating possibility. Perhaps what we think of as empty space is actually one of the richest and most complex aspects of reality. The of another discovery challenged our understanding even further: quantum entanglement. To appreciate why this idea is so remarkable, Imagine two perfectly synchronized clocks created together. You place one clock in London and another on the opposite side of the world. When you examine them later, you find correlations between their behavior that seem unexpectedly connected. This analogy is imperfect, but it hints at the surprise physicists felt when studying entangled particles. Quantum systems can become linked in ways that appear to transcend ordinary expectations about separation. Even decades after its discovery, entanglement remains one of the most intriguing features of quantum theory. It does not allow messages to travel instantly across the universe. That common misconception is important to avoid. Yet it reveals that reality may be more deeply connected than everyday experience suggests. Some modern theories go even further. A growing number of physicists have explored the possibility that quantum entanglement may play a role in constructing the very fabric of space itself. In this view, space may not be the fundamental stage upon which physics occurs. Instead, space could emerge from deeper relationships hidden beneath reality. The idea remains under investigation, but it points toward a profound shift in perspective. Perhaps space is not the foundation. Perhaps it is the result. As physicists continue descending toward smaller scales, they eventually approach a realm where current theories begin to struggle. A scale so tiny that human intuition completely fails. To visualize it, imagine taking a photograph and zooming in again and again. At first, the image appears smooth. Then individual pixels become visible. The picture that once seemed continuous reveals an underlying structure. Some researchers wonder whether space-time itself may behave in a somewhat similar way. Not perfectly smooth, not infinitely divisible, but composed of fundamental units beyond which ordinary concepts lose meaning. One idea associated with this possibility is known as quantum foam. The name was introduced by the physicist John Wheeler. It describes a picture of reality at unimaginably tiny scales. Rather than smooth and calm, space-time may resemble a turbulent sea, tiny fluctuations continuously forming and dissolving, bubbles appearing and disappearing, geometry itself becoming restless. Imagine standing beside an ocean. From a distance, the surface appears smooth, but as you move closer, countless waves, ripples, and bubbles become visible. Quantum foam suggests that space-time itself may possess a similar hidden texture. At the scales of daily life, this texture remains invisible. The world appears stable and continuous. Yet beneath that appearance, reality may be far more intricate, and the surprises do not end there. Seen. This idea can feel deeply counterintuitive. After all, time seems fundamental. We experience it constantly. Moments pass, days unfold. CESO life itself appears woven into the flow of time. Yet history offers many examples of things that once seemed fundamental, but later turned out to emerge from deeper processes. Consider temperature. For centuries, people experienced warmth and cold without understanding their origin. Today, we know that temperature emerges from the motion of countless particles. The phenomenon is real, but it is not fundamental in the way people once imagined. Some researchers wonder whether time might be similar. Perhaps what we experience as the passage of time emerges from more fundamental relationships hidden beneath reality. If true, then one of the most familiar aspects of existence may arise from mechanisms we have only begun to glimpse. The universe revealed by quantum physics is therefore not merely small, it is profoundly strange. Empty space is active, particles resemble ripples, entanglement hints at deep connections, space-time may possess hidden structure. and time itself may not occupy the role we once assigned to it. The deeper we travel into reality, the more the universe seems to transform from a collection of objects into a web of relationships. A place where familiar concepts gradually dissolve and new possibilities emerge. And some of those possibilities lead toward ideas so extraordinary that they challenge our very understanding of what reality might be. By this point in our journey, the universe has already revealed itself to be far stranger than it first appeared. We have explored invisible matter shaping galaxies. We have encountered black holes that distort time. We have seen how empty space may not truly be empty. And we have ventured into a quantum realm where reality behaves in ways that challenge common intuition. Yet some of the most extraordinary ideas in modern physics lie even further beyond the horizon. These ideas occupy a unique place in science. Some emerge naturally from established theories. Others remain highly speculative. Some may eventually prove correct. Others may not. But all of them share a common purpose. They attempt to answer questions that continue to linger at the edges of our understanding. They are, as we discussed earlier, many cosmologists believe the universe experienced a brief period of astonishing expansion shortly after its beginning. This process, known as inflation, helps explain several important features of the cosmos. But some versions of inflation lead to an unexpected possibility. According to certain models, inflation may not have happened only once. Instead, it may continue indefinitely in distant regions of reality. While inflation ends in one region and allows galaxies and stars to form, other regions continue expanding. The process repeats again and again. The result is an idea often called eternal inflation, a cosmic landscape in which countless regions may exist beyond our observable horizon. Each region could potentially develop its own history, its own galaxies, its own stars, its own cosmic story. This idea naturally leads to one of the most famous concepts in modern cosmology, the multiverse. The word itself captures the imagination. Rather than a single universe, there may be many, perhaps countless, perhaps infinitely many. It is important to emphasize that this remains a theoretical possibility rather than an established fact. At present, no direct observation has confirmed the existence of other universes. Yet the idea continues to attract attention because it emerges from mathematical frameworks that successfully explain other aspects of nature. Whether the multiverse exists or not, it reminds us how quickly familiar assumptions can expand into something much larger. Another possibility involves dimensions beyond those we experience in daily life. Most of us think naturally in terms of three dimensions of space: length, width, height. Combined with time, they form the stage upon which our lives unfold. Yet, some physical theories suggest additional dimensions may exist. Not because scientists enjoy making reality more complicated, but because the mathematics appears to allow such possibilities. A useful analogy involves a garden hose viewed from far away. At a distance, the hose appears one-dimensional, a simple line stretching across the ground. But as you move closer, you discover another dimension wrapped around its surface. An ant crawling along the hose experiences more directions of movement than someone observing from afar. Some physicists have wondered whether something similar could occur in the universe. Additional dimensions may exist while remaining hidden from ordinary observation. This possibility appears in versions of string theory. String theory proposes that the fundamental ingredients of nature may not be point-like particles, but tiny vibrating entities. Different vibrations would correspond to different particles, a bit like different notes emerging from the strings of a musical instrument. Whether string theory ultimately describes reality remains uncertain. Yet its imagery offers a fascinating perspective. A universe in which matter and forces arise from deeper patterns of vibration. As intriguing as extra dimensions may be, another idea pushes even further: the holographic principle. At first hearing, the concept sounds almost impossible. Imagine looking at a three-dimensional object, a sculpture, a mountain, a person standing beside you. Now imagine that all the information needed to describe that three-dimensional reality could somehow be encoded on a two-dimensional surface. That is the essence of the holographic principle. The idea emerged from attempts to understand black holes and information. Over time, physicists discovered surprising mathematical connections suggesting that a higher dimensional region may sometimes be described by information stored on a lower dimensional boundary. This does not mean the universe is literally a giant hologram in the everyday sense. Yet it suggests that our intuitive understanding of space may not tell the whole story. Some researchers have explored a broader interpretation, sometimes called the holographic universe. In this view, the reality we experience could emerge from deeper informational structures. Space, distance, even aspects of gravity might arise from relationships hidden beneath the surface. Although these ideas remain active areas of research, they illustrate a recurring theme in modern physics. Again and again, concepts that once seemed fundamental become part of a deeper framework. The deeper we investigate, the more reality appears layered. This naturally brings us to another famous possibility: the simulation hypothesis. Unlike many ideas discussed in physics, this concept occupies a more philosophical territory. It proposes that sufficiently advanced civilizations might one day create detailed simulations of conscious beings and entire worlds. If such simulations became common, some philosophers have argued that simulated realities could outnumber original ones. The idea has generated widespread discussion, yet it is important to approach it carefully. At present, there is no scientific evidence demonstrating that our universe is a simulation. The concept remains a philosophical thought experiment rather than an accepted scientific conclusion. Its value lies less in proving a claim and more in encouraging reflection. How do we know what is fundamental? What counts as evidence? What assumptions do we make about reality without realizing it? These science thrives when imagination and evidence work together. Imagination generates possibilities. Evidence determines which possibilities survive. History contains many examples of ideas that initially seemed impossible, but later proved correct. It also contains countless ideas that turned out to be wrong. The challenge is learning the difference, and that process takes patience, observation, experiment, time, spread. It is that reality has repeatedly proven more surprising than expected. Galaxies beyond galaxies, invisible matter, expanding space, black holes, quantum entanglement. Each discovery once seemed extraordinary. Each eventually became part of our evolving picture of the cosmos. And so, as we stand at the edge of present knowledge, we find ourselves in a familiar position, looking outward into darkness, aware that much remains unknown, wondering what future discoveries may reveal. Because if history teaches us anything, it is that the universe often turns out to be stranger than even our boldest expectations. And nowhere does that strangeness become more profound than when we ask what will happen to the cosmos itself in the unimaginably distant future. When we look up at the night sky, it is easy to imagine that the universe has always looked roughly the same. Stars shine, galaxies drift through space, new worlds form around young suns. the cosmos feels timeless, stable, enduring. Yet the universe is changing every moment. Most of those changes happen so slowly that a human lifetime is far too brief to notice them. But given enough time, even the grandest structures in existence begin to transform. Our story begins relatively close to home. Far beyond the stars, visible to the naked eye, lies the Andromeda Galaxy, the nearest large galactic neighbor to the Milky Way. For Millie today, careful measurements reveal something surprising. It is moving toward us, not rapidly by everyday standards, but steadily on cosmic timescales. Billions of years from now, the Milky Way and Andromeda will meet. At first, the word collision sounds catastrophic, yet galaxies are mostly empty space. Identify as the two galaxies pass through one another, direct stellar collisions will be relatively rare. Instead, gravity will reshape both systems. Spiral arms will stretch and distort. Stars will follow new paths. Over immense periods of time, the two galaxies will gradually merge into a single larger galaxy. Future observers, if any exist, may see a very different sky from the one above Earth tonight. Yet even this dramatic event is only a small chapter in a much larger future. The expansion of the universe continues, and according to current observations, that expansion is accelerating. Over billions and trillions of years, distant galaxies will move farther away. Eventually, many will recede beyond our observable horizon. Their light will never again reach our region of space. At first, you can see every detail, then only the sails, then tiny specks on the horizon. Finally, nothing at all. A few. Many of the galaxies visible today will have disappeared from view. The universe will appear lonelier, smaller, more isolated, yet estee. Some of the smallest stars burn their fuel so slowly that they can survive for trillions of years. These quiet red stars are remarkably efficient. They consume their fuel carefully, like a candle that barely flickers. But even they cannot shine forever. Eventually, the supply of fresh gas needed to create new stars will diminish. Galaxies already convert enormous amounts of gas into stars. Over vast stretches of time, those reserves will be depleted. The era of active star formation will gradually come to an end. The cosmos will grow darker, not suddenly, no, but slowly, almost imperceptibly, like a city whose lights are extinguished one by one across an exceptionally long night. This distant future is sometimes called the degenerate era, a time when most brilliant stars have already lived and died. The universe becomes populated primarily by stellar remnants, white dwarfs, neutron stars, black holes, ancient objects preserving the memory of earlier cosmic ages. If enough time passes, even these remnants continue evolving. White dwarfs cool, neutron stars gradually lose energy, black holes remain. For a while, they may become the dominant structures of the cosmos. To many people, black holes feel permanent. Yet one of the most surprising insights from modern physics suggests otherwise. As we explored earlier, black holes may slowly emit Hawking radiation. The process is extraordinarily slow. A black hole containing the mass of a star would require periods of time so vast that ordinary numbers lose meaning. Yet according to current theory, black holes do not last forever. Given enough time, they gradually evaporate. The final black holes may outlive stars by unimaginable durations, yet eventually even they disappear. When physicists calculate the far future of an ever-expanding universe, they arrive at a scenario often called heat death. The name can be misleading. It does not mean the universe becomes hot. In many ways, the opposite is true. The concept refers to a state in which useful energy differences have largely vanished. Star complex processes become increasingly rare. Matter grows more isolated. The universe drifts toward a condition of maximum equilibrium. Imagine a cup of hot tea left untouched on a table. Over time, the tea cools. The temperature difference between the tea and the surrounding room gradually disappears. The system becomes more uniform. Heat death describes a similar trend occurring across the entire cosmos. Not tomorrow, not in billions of years, but over timescales almost impossible to comprehend. The universe may slowly become quieter, darker, more uniform. Yet heat death is not the only possibility scientists have considered. Some theories suggest dark energy could change over time. Others propose that unknown physical processes may alter the long-term future. There are scenarios involving cosmic cycles, scenarios involving quantum events, scenarios involving transformations we do not yet understand. At present, the evidence favors continued expansion, but the final fate of the universe remains an open question, and perhaps that uncertainty is fitting. Throughout this journey, we have repeatedly encountered the unexpected. The universe turned out to be larger than imagined, older than imagined, stranger than imagined. Invisible matter shapes galaxies. Black holes bend time. Quantum fluctuations may have seeded cosmic structure. Reality itself may possess hidden layers beyond ordinary experience. Again and again, nature has expanded the boundaries of possibility. And yet, despite all these discoveries, there remains something wonderfully simple about our place within the story. Every atom in your body was forged through cosmic history. The oxygen you breathe, the calcium in your bones, the iron carried through your blood, all were shaped by ancient stars long before Earth existed. You are part of the universe contemplating itself. A brief awareness emerging from a cosmic process, billions of years in the making. Perth. Not that humanity stands apart from the cosmos, but that humanity belongs to it. The same laws that guide galaxies also guide the atoms within us. The same history that produced stars ultimately produced the minds capable of wondering about them. And so, as our exploration gently comes to rest, the universe remains what it has always been, to pay a place of beauty, a place larger, older, and stranger than any single imagination can fully contain. Somewhere beyond the stars, galaxies continue their slow journeys through darkness. Ancient light continues crossing space. Black holes quietly shape their surroundings. And the cosmos carries on with its vast, patient story. If you are listening while resting, perhaps let that thought drift softly through your mind. You do not need to solve the mysteries of the universe tonight. It is enough simply to wonder about them. And perhaps, as the stars continue their silent motion above, you can allow your thoughts to grow a little quieter, a little calmer, like distant starlight fading gently into the night. Thank you for joining this journey through the cosmos. Wherever your thoughts may wander next, may they do so peacefully. And for now, beneath this vast and mysterious universe, good night.